Started. We're recording. Okay, perfect. So as I said, today is going to be about imaginaries in ACVF. So I'm not going to prove everything because well, I only have an hour and a half left, and it's well, the proof probably would require 3 hours. But I'm at least going to try to give an idea of what's going on, and hopefully it will be enough of an idea that you're happy with it. So so first remark, last time we proved that if we have a map from K and gamma n into K, then it has finite image. Okay, so this is exactly saying that you can't eliminate K or gamma as imaginaries. Okay, because well, you can't possibly embed, or even K gamma. You can't possibly embed K into a big K. It's not possible. Oh yes, you're right. No, I forgot to remove. You can't possibly do this. So this immediately shows that imaginaries, if you want to eliminate imaginaries, you at least need to have K and gamma around. So at least big K, little k, gamma. And in fact, there's more than that. Why did I put a line here? It's the next one that needs a line. There's even more than that because now, so I'm not going to prove that these exist, but if you take a ball,
in principle, you could eliminate nothing K, but if you treat one of the others as
well, yeah, but what do you mean? That you could maybe eliminate little k into gamma, but they're orthogonal. Yeah, you're right. Okay, you're right. But yeah, so I mean, I'm not trying to be completely specific, but I'm just so there is an actual theorem that well, anyway, I'll come back to this. But now, if you take, I'm not going to prove that these exist, but you can find balls. So you can find a ball. So you take M, a model of a large enough model of ACVF, and you can find a ball such that that has no point over its code. Okay, so essentially what it amounts to, which isolates a complete type over its code. So I won't show that these exist, but you can find them. And now, if you look at so it's code that I'm going to write. So yes, tell me. So since imaginaries have been talked about by at least Rahim and Anand by now, I'm not redefining any imaginary related terms. But if there is any, if I'm using any terminology that people are, well, maybe codes weren't explicitly defined, so maybe I should do that. So if I have X, a definable set, I define code of X in MEQ. So then I define code of X in MEQ to be the DCL, so the DCL-EQ of any canonical parameter. And since any two canonical parameters are interdefinable, this is a well-defined set. So DCL-EQ of, well, so code of B intersect K union little k union gamma is essentially going to be nothing. Okay, so what it's going to be, it's going to just be, well, you always have DCL of the empty set.
You have parentheses somewhere in the intersection.
Yeah. So, I'm just saying
Silvain,
what
is B here?
it's a ball.
Okay.
Closed. Closed ball. Yeah, I wrote it and then I erased it, I think. Yeah, so of course you have DCL of the empty set, and then you essentially have nothing more in K and gamma, and then you have gamma of DCL of the radius of B. This also can be shown by an automorphism argument because, well, you can move things around a lot because, well, you have very few points related to B. So
you don't want a particular ball that has, you're not saying all balls.
no, all balls will that isolate a complete type have this property.
Right.
Yeah. So if I have a ball that isolates a complete type, then I have this property. Because essentially, points inside the ball I can just move around because it's a complete type. Points outside the ball I can move around because that I can always do. Except if they're in DCL of the empty set, of course. And then you have to show that essentially you can't define anything in K, but it's the slightly tricky part. And then you have to show that the only thing you define in gamma is the radius. But so there's a few things to say. I'm not claiming this is easy, but I'm just trying to at least give an idea of what sort of other imaginaries can appear. And so I claim this shows that now B is an imaginary that I can't eliminate, because I definitely can't define B using just DCL of the empty set and its radius. Okay, because there are many other balls that have the same radius. So yes, and B, and this is not enough to define B. So essentially, the only point I was trying to make is that we also have the space of balls somehow. I mean, we need to take into account the space of balls. So of course, certain balls can be coded because, well, the valuation ring O is coded by the empty set because it's empty set definable. But so certain balls can be coded, of course, but in general, they can't. Yes, Yaki.
Part of it can be to show like that the ball doesn't intersect the CL of the
Yes, but if it intersected the CL of the empty set, it would not isolate a complete type.
Can you say something about which balls have properties of the isolated complete type?
Yeah, essentially all of them. But how can you do it? Most of them do, but take a small ball with radius transcendental, with infinitesimal radius, and that does not intersect the CL of the empty set, then it will have this property, I think. Maybe it does not intersect ACL of the empty set to be safe, but yes, of course, you need ACL of the empty set, but then I think this will work. I mean, I'm not claiming I can do the proof out of, but a lot of them have this property. Yeah, I guess I think any ball that avoids ACL of the empty set will have this property, I think. Yeah. Okay, maybe I'm getting ahead of myself, but it's not a rare phenomenon. Okay, good. So we need so it's not even enough to have. So I mean, seeing how the theory was developed, we kind of expected to need at least K and gamma, but these are not enough. We need more than that. And in a way, balls, closed balls at least, are like affine. So gamma is what it does is encode closed balls centered at 0. We can see it this way. And so what we're saying here is that we need affine versions of this also. And as we know, doing affine versions of things essentially amounts to doing linear versions of things in higher dimension. And then it goes up. So what we're going to do now is to try to give higher dimension versions of little k and gamma. So I'm going to do, so let's fix an n, a strictly positive integer. And
Silvain, what if you just add all balls?
yeah, but that's still not enough.
Oh, it's still not enough.
I'm not going to prove that because it gets more complicated, but adding all balls is still not enough. So so this is related to Rahim's question, and I'm also going to once I've written I'll come back to that question. So I'm going to define Sn to be the space, the set of all free rank n submodules, O submodules of Kn. So what the free rank n means that I take a basis of Kn and I look at the O submodule generated by it. Okay, so this for now is just a set, but it's not very hard to see that it's an interpretable set exactly for the reason I just gave, because it's parameterized by choosing a basis here. So this is the same as GLNK mod GLNO. Okay. So if you want, you can. Another way of seeing it is that GLNK acts on this set by just sending a lattice by it acts on it in the linear way, and the stabilizer of every point is GLNO. So that's the first set, and so maybe a little remark: we're in known territory because what is S1? S1 is K cross mod O cross, so it's just gamma without the infinity. Okay. So we're in known territory, except now we're higher dimension, and you can check by the usual coding affine things into linear things trick that the space of balls lives in S2. So S2 contains contains up to ISO, of course. So so maybe I should say S2 allows to code all balls. Okay, so what do? You see B as a coset of a lattice in dimension 1, and you encode the lattice in dimension 1, this coset in dimension 2 by seeing it as so what do you take? You add a 1 somewhere in the matrix and 0 elsewhere. I mean, it's the usual coding trick for affine lines into 2 space. So S1 at least solves the problem I had above. It doesn't solve the problem of open balls though, which you essentially have the same problem because I said closed ball, but you have the same problem with open balls. Good, so then we need a second set of imaginaries. Because essentially what we've done is mimic gamma in higher dimension. So now we want to mimic K in higher dimension.
What's this trick? When you say higher?
Well, if you want to, so if you have a line, how do you encode it as a vector space in dimension 2? You just your line is A plus bx, and you do something like BA10, something like that. If you look at the vector space given by that, if you intersect it with the plane at 1, you get the line. Maybe my matrix is wrong, but I mean it's completely standard, and I can try to remember it. But I think it's. I mean, I'm not sure my ones and my zero are in the right place, but I think it's something like that. Or maybe a and one are inverse, but essentially yes. So what I'm saying is that the drawing is easier. It's clear. If you have, well, the drawing is easier maybe to understand. If you have, so what you do is you have a line. So you have a line, and then you look at coordinate 1, and you see that line inside the space in coordinate 1, and then you look at the plane generated by this line and the yes, the line given by the plane given by this line and the origin. It's going to give you a linear surface, and this is the one I'm trying to describe here. And you can do the same thing now with the O modules. So the second set we want to consider is called Tn, and so it's the union. Actually, it's a disjoint union, but it's naturally a disjoint union. But okay, whatever. So you take every lattice in Sn, and you look at what it looks like when you reduce it mod ms. So it's the set of m cosets of S inside of S. Okay, so once again, what is T1? T1 is someone we know. T1 is actually, okay, maybe before I do that. So this is very clearly an interpretable set, but we can also see it as a coset of GLN, because GLNK acts on this thing. How? So, well, actually, well, yeah. So you can have GLN act on this in the reasonable way, which is that you take a coset and then you find a basis. So if it's okay, maybe there's one annoying thing, which is MS itself. So you just the action on MS is so maybe let me remove MS. So now, how do you make GLN act on this? You take a coset, so it's a non-zero coset, so you can complete it into a basis of S. And now you act on the basis, and you look at the first coordinate. It's going to give you a new non-zero coset of a new lattice. So that's how GLN acts. Of course, you could also have it act on this one by just sending it to n times whatever new thing you get out of a basis of this. But it would just create a new orbit of the action, so we don't really care about it. What? M is the maximal ideal. It should be frac somehow, but it's maximal ideal. Yes, and so GLNK acts on this, and you can and
Silvain, can you explain again what is this set? It's the union, so every element there is itself.
You take a lattice.
Mm-hmm.
So you take a O module, and then this is another O module, and you get the quotient.
Yeah, but the Tn itself is the family of those quotients, or is it the union of those quotients? What do you mean by union of? So if you have
it's all cosets. I mean, a point in Tn. Yeah. So maybe I should. Okay, if you want to be extremely precise, it's the data of this. I mean, it's the disjoint. It's the disjoint union. So you remember. Sorry about this. Are you still hearing me? Perfect. Sorry, I'll stand less close. You also the real data is a coset plus the S out of which it's a coset of, but you can actually recover it from it. But you could also be explicit. It's not a matter. Does that answer your question? So this is what I mean by that is the set of A plus MSS, where S is in Sn and A is in S. If we are very, very explicit, this is what this is. Okay, so it's all possible cosets. What? A is not in an S. Although you could put it, it's just then you have another copy of Sn around. It's not that dramatic.
So in this notation, can you explain again the action?
Yes. So if you take an A, you can make it into you can complete it into a basis of S. So A0, AN, where this is a basis of S. And then you take the previous action. And so you can GLN acts on this because this is a basis of K. It's actually a basis of Kn. So it's an element of GLN. This is an element of GLNK. So GLNK acts on itself. And how do you recover an element of Tn is well, you just take. So if you have an element of GLNK, you see it as a basis of an O module that gives you the S, and you look at the first coordinate, it gives you the coset. So that's how you act on this thing. And so if you then the stabilizer is always the same. And so in fact, what you see is that Tn is GLNK mod a group that I'm going to call GLN NNO. Who cares? We just need to give it a name. So what is this group? It's well, maybe I should call it GLN. Yeah, here I'm using the first coordinate, so probably I should call it 1. So that's matrix. That's elements of GLN O, such that the first coordinate, the first column, reduces to 0, 0, and 1 on the diagonal. So 1 on the diagonal, sorry. 1, 0, 0, 0. Reduces mod M. You can check. This is the stabilizer. And so now, it's even easier to see once you see it as this quotient. What is T1? Well, it's K cross mod. So here you only have one diagonal coefficient, so you have to reduce to 1 mod M. So it's K cross mod 1 plus M, which is our dear friend RV. Well, maybe RV cross, because in RV I added a 0. And the 0 is essentially the fact that you remove this thing. It's the same phenomenon. Good. So at least T1 we already encountered. I pretend that in T2 you can code all open balls. But then the theorem, the main theorem is the following. So in particular, since we have RV, we also have the residue field. So we've not lost the residue field, but we have more than that. And I should point out, because that's extremely important, I forgot. This is in fact a K vector space of dimension n. Yeah, small k. It's supposed to be a small k. So what we're looking at is families of vector spaces of dimension n. I never quite described it, but RV is also a family of vector space of dimension 1. It's not very hard to see. And I didn't describe it this way before. But anyway, so back to the theorem of Haskell, Shosky, and McPherson. So ACVF eliminates imaginaries in the sorts K, Sn for len, Sn for len. So what do I mean by that? I mean that i.e. if you take E in MEQ, where M is a model of ACVF.
Wait, are there any maps? You take the natural map.
I mean, K, Sn, and Tn live in MEQ. So yeah. So that I'm going to explain to you what I mean by that statement. It's not. I'm not saying that this is a language. I avoid speaking about a language by working in MEQ. But no, of course. Okay. Yeah, that's okay. I'll finish this and then I'll answer your question. So yes. So all n positive. That's important. M is in ACVF, then E is defined. Well, then there exists D in DCL of E intersect. Well, it's a tuple K union all the SNs. It's a finite tuple, but so yeah. Finite tuple such that, I mean, it's obviously finite since such that E is definable over D. Okay, so every imaginary can be coded in these sorts. So now if you want a statement in terms of languages, you can define the geometric language, which has sorts K, Sn for len, Tn for len. This you put the ring language plus the divisibility predicate, so that you have the full structure on K, and then you have a map little sn from gln K to Sn, and a little map Tn from gln K to Tn. And I probably also, let's put it map tau n from Tn to Sn, although I don't think I need it, but let's put it in anyway.
You don't need any other.
No, because you only need to know that what quotient they are, because then the structure is going to be fully induced by this. Yeah, so I think the Theorem is actually definable in all of this, so you can forget it. Let's forget the Theorem. Because Theorem is just, I mean, it's obviously definable from SNMT. Anyway, okay, so if you want, you can reformulate now ACVF in this language eliminates imaginaries in the usual sense. Okay, but yeah. Tn is this family of K vector spaces. But no, Tn. Remember, Tn is isomorphic to a quotient of GLN K. So that's Tn. So I identify it with a quotient of GLN K. Yeah, but you get the group structure because it's induced by the group structure on GLN-K. Well, you don't get the group structure because this GLN neither are normal, except in dimension 1. So in dimension 1 you get a group, but in higher dimension you get so you get a fibration of vector spaces in one case, and you get something in the other case. So
this first column reduces to 1, 0, 1, 0.
What?
What is it in the first column?
Oh, no. It's sorry. 1 on the diagonal and 0 everywhere. Yeah, that was.
So what you mean is that what in this language and this sort, you have full elimination.
Yeah, so if you want ACVFG, eliminates imaginaries. Where ACVFG is the theory of ACVF written in this language. But I tend to prefer this sort of result because I mean, I prefer written it this way because we all know that what we're really trying to identify is a minimal subset of EQ that works. The actual language we use matters very little. No, so if you now want to explain what's the structure on SN, then what you would want is a quantifier elimination in these sorts, and that's much harder. I mean, I don't know any completely satisfactory one. The structure on SN is still quite a mystery, at least to me, I think. But anyway, so in Haskell-Rorschowski-McPherson, they do give a quantifier elimination result. The structure on the SN is better than just the Morley structure, but it's essentially like the generically Morley structure. So it's not that satisfactory in terms of describing what it is. So yes, so the remark that answers both Itai's question and Rahim's question is that this is a minimal set. So Haskell-Rorschowski-McPherson also proved that any subset of those are not enough. So K, SN, Tn for fixed. And because you can easily see Sn as a subset of Sm for m bigger. So really the question is this enough? Or maybe if you want to, maybe yeah, let's even make the stronger statement for fixed m is not enough. I'm not going to give you the example, but you can do something slightly similar to this. You take a higher dimension module, and you make a few assumptions so that it doesn't come from lower dimension things, and then this can be encoded. Good. So that's the theorem I want to prove. I'm of course. Oh well, I have an hour to prove it. I'm not going to prove it in an hour, but hopefully I'll give enough of an intuition as to at least why these sorts, how these sorts come up, and also maybe why they're sufficient. But and so yes, so the first thing to note is that I'm not going to do the original Haskell-Rorschowski-McPherson proof because this would definitely not fit in an hour. Because to prove that theorem, they developed a very interesting theory of table domination, and then they used this to eventually eliminate imaginaries. But in fact, in retrospect, you don't really need table domination to prove that theorem. And there's been new proofs of that result. So first one by Rorschowski, which already simplified a lot the initial proof, but still use table domination, and then a further proof of Johnson that refines it even more to completely, I mean, to an almost elementary proof for a certain definition of elementary. I mean, you essentially use no complicated tools other than what's a definable set, a definable type. So how do definable types come up in this picture? It's in the following way. So somehow an important insight of Rorschowski's second proof of the theorem is that, well, it's also omnipresent in the first proof, but it's hidden because they're using more complicated types, is that somehow encoding sets is annoying. You want to code types instead. Encoding types is easier. So the problem is that most types are complicated infinitary objects. So the types that where you have a chance to actually encode them is the definable ones. And so now if you want to use definable types to code every set, you need to know that you have a lot of definable types. And this is essentially what this proposition of Woody says. So let T be a theory with dominant sort D, or maybe let's call it K because it's K. Okay.
So what
So
does
what
that
do I
mean?
mean by that?
Oh,
Yes. Yes, Itai? No.
I was just asking, what do you mean by that? Yes.
Yes. So I just mean that every sort of T comes with a surjection from a Cartesian power of K. So essentially, what we're saying is that just T is just some part of the EQ of the theory induced on K.
So is it so maybe it's enough to say the proposition where K is the home sort?
It's yeah. I mean, it's a definition of home sort.
Okay.
I mean, what is the home sort when you have multiple sorts?
Yes, right.
So of course, if you have a single sort, the sort is dominant, and the set of all sorts is always dominant. But here I'm trying to be a little more precise, such that so one every definable so with parameters set X inside of K1, so unary subset of K, is consistent with, well, actually contains, but okay, whatever, with code of ICL EQ of code of X definable type P. So here, of course, here I say consistent, but in fact, you actually P concentrates on X because it's a complete type. Okay, so okay, so this, of course, is true in any stable theory. This is not. This is just extension of non-forking. Two, every definable type P is in fact ACL EQ of code of P. So I'm going to define code of P in a second, but you can imagine what it is. ACL EQ of code of P intersect so how do I want to note that? Intersect the real sorts of T. Intersect S, where this is the set of all, this is the set of sorts of T definable. Maybe I should call them R because they're the real sorts. Okay, so what I'm saying here is that, so yes, so let's define this thing. So P is definable, so you get, for every phi, you get a formula dpx phi xy, which is a formula in Y, which is definable. And the code of P is just the collection. It's the union for phi of the code of these things. Okay, so this is a definable set. And you take its codes, and you take all the codes for all the definable sets. So it's really, I mean, it's just the smallest definable, the smallest DCL closed set over which P is definable. Good. Is that clear? I mean, the notation are a bit annoying, but I hope this is clear enough.
It's clear that it's DCL closed.
No, I mean,
You
the
want
DCL
to-
of that is, yeah, the DCL of that. Yeah, maybe I want the DCL of that, you're right. Okay, so that's number 2. Then T has weak elimination of imaginaries. So of course, now if you add 3, every finite set is coded, you get elimination. If 3, every x, every finite x in Cartesian products of real sorts, also of sorts of T, is coded. So by which I mean it's this is just saying that x is code of x intersect R definable. Then T has elimination of imaginaries. And if you look at this proposition, at least in the stable case, it's kind of how a lot of proof of elimination of imaginaries were actually proved. Sometimes it's a bit hidden that it's what you're doing, but what you often, number one in a stable theory is always true. And so what you have to do is to code definable types. And for example, in ACF, you show that types are coded by the ideal, and then you take the minimal field of definition for the ideal, and here you are. And then you have to code finite sets.
Silvain, the special sorts, the home sorts are there are okay. What's the
No. So there's two. R is the set of all the sorts of T, and K is the home sort.
oh
Is
okay.
the special sort where everything comes from. So yeah, if you want, I could have formulated it in. I just take a theory T of sort K and a set of sort R, and then I can explain the conclusion with be T has a weak elimination of imaginaries in R, and T has elimination of imaginaries in R, if you prefer. I mean, if you want to work in TEQ directly. But, so the K is just to simply to make hypothesis 1 even nicer. A priori, we would have to do it for every sort of T, but we only need to do it for one out of which you can create all the others. It's just to make one nicer. So maybe a quick proof of this. So first, let's assume 1 prime. Let's assume the stronger version. So every definable set X in Cartesian powers of sorts of P of T is consistent. So if this holds, is consistent with an code of ACLEQ X definable type P. So I claim that 1 implies 1 prime, but I'll let you think about it, and I'll eventually come back to it. But the really interesting proof is, I think the really interesting proof is how do you get elimination of imaginaries out of 1 prime, well, weak elimination of imaginaries out of 1 prime and 2.
You mean not just power, but products of different sorts.
Yes, Cartesian products. Yes, you're right. Sorry. Yeah, here also. Oh yes, products. I did write products with that. Yeah. So you take every definable set in T instead of just the ones that live in the unary ones in the home set. This is, I mean, going from 1 to 1 prime is essentially an application of transitivity. I mean, it's a bit more than that, but I can come back to it. Yeah, so now it's quite easy what you do. So, well, let's take M model of T, E in MEQ, and you have an F from, well, actually you can take it from Kn, but it doesn't really matter. Do I want, does it really matter? Well, okay. Well, so you have some definable function f. Definable in where x is a bunch of real sorts, and y is the sort where E lives. Definable such that zero definable, such that E is f of A for some A. Okay, so this is nothing. It's just saying that imaginaries are just quotients of real things. Yes. So now.
But you can also take it in K, no?
Yeah, I could take it in K. Yeah, I could take it in K. Yeah, I agree. If you want, this is Kn. Yeah, I agree. Now, let x. So in fact, I only need 1 prime inside Kn now if I do that. But okay, what it doesn't really matter. X is yes. So x is f minus 1 of E. This is a definable set that lives in Kn, and out of 1 prime, I get a type P, which is code ACLEQ of code of X definable. So in particular, it's ACLEQ of E definable. Okay. Now I apply 2. And so P is in fact R intersect ACLEQ of E definable. So let's call that big E. And now I claim that little e is big E definable. Why? Because if I take an automorphism of M over big E, then sigma of P is P. So I really only use that P is invariant, to be fair. So sigma of P is P. And so.
Wait, can you do it a little bit slower?
Yes.
Okay, so when 2 P's are intersecting, so the E.
And I just call that E, big E.
Sorry?
I call that
You
big
call
E.
it- Okay.
There's only two.
Yeah.
Oh, yeah. Do you want me to call it big A, maybe?
Big A, so-
So remember, we want to prove weak elimination of imaginaries. So what we want to prove is that E is in DCLEQ of A. This is exactly weak elimination of imaginaries.
It's enough ACLEQ, no?
No, that would be
Weak.
geometric elimination.
Yeah, right.
Weak elimination is any element is definable over the algebraic closure in the real point, over its algebraic closure in the real source. Okay, so what we want to prove is that E is in DCLEQ of A. And so what we're going to show is that whenever we have an automorphism sending, fixing A, it sends E to E. But what we know is that it sends P to P. And remember, P lives in X. So since sigma of P is equal to sigma of P also lives in X. But E is f of X. So now sigma of E. So if you want, yes, so P, maybe I can rewrite this. P says that f of x is equal to E, but sigma P also says it. But sigma P says that f of x is equal to sigma of E, and it also says that it's equal to E because it's equal to P. Okay, so sigma E is equal to E. Or maybe, I mean,
You meant on the left.
sigma P equal to P implies f of x equal to E, and sigma of P implies that it's equal to sigma of E, and so both of these are equal.
Implies.
Yes, sorry. Okay, so we've proved that any automorphism fixing A fixes E. So we've proved this, and this is the end of our proof. So why is Y prime true? It follows from two facts. So first, notice that you only have to prove one prime for k to the n, but that's easy. So because well, if you have a set that lives in other sorts, you just pull it back to k to the n using the zero definable surjections. So suffices, which is essentially what we've done just here anyway, when I put k in here after get here. We may assume A lives in k of n. Okay, and so first thing we do is we project it on the first coordinate. So that's the projection on the first coordinate. And so now we apply 1 and we find P. P, which is a CLEQ of code of X definable. Let me give that a name because I'm going
Wait,
to use
not
it
the
a lot.
code of X, the code of the projection.
But yeah, but the code of the projection is in particular defined on the code of X.
Oh
So
yeah.
this is definable with P implying x0. Okay, and so now what we want to do is realize P, look at the fiber above it, and apply 1 again. This does not work because there's something here. We take an ACL, so we have to be a bit careful. So first, we need to prove a small thing, which is that if we take any C in ACLEQ of code of X, so take A realizing P over some model M0. And if we look at C in here, then the type of C over M0 is also ACLEQ of code of X definable. This is not very hard, but you have to prove it.
So M0 is just a model?
Yeah, it's a small model. And so now, so this maybe this is an exercise. It's not very hard. It's the kind of things. I mean, it's a variation on the finite equivalence theorem relation. I mean, on the finite equivalence theorem. Yes, And so now you just look at pi minus 1 of A, which is just, so it's the fiber of this map over A, and by induction you find Q, which is consistent with this thing. Let's call it Y. And which is what? Which is definable over the code of this, but the code of this, what it is, it lives inside code of X and A. So that's why we have this thing here. Definable, yes. So Q is ACLEQ definable. Yes, and so now what you do is you take a realization of Q over a realization of P. This is going to give you a definable type, and it will live in X. Okay, so if you take B, realizing Q, so you take M, you have M0 inside, well, M0A inside M1. You take another small model. You take B that realizes Q over M1, and I claim that the type of AB over M0 is definable. So it's ACLEQ of code of X definable. This is, this is transitivity for definable types. So that allows you to go from 1 to 1 prime. And I think now is the time for the break.
Wait, what did you use C in this proof?
What?
What did you use C? There was C, and now there is no C.
No, sorry. You're right, I lied. Sorry, so yes, you're right. So this is C. Sorry. So the type of C over M0 is by the exercise also ACLEQ of code of X definable.
What do you mean you find C4, you find the element?
Yeah, but I take all of it.
Oh, okay.
Actually, if you want, this is a couple.
This was for NC, okay, I wanted as 6.
Oh, yes.
And how do you even know that the type of C is definable?
That's your exercise type.
So it's not only about finite equivalence relation theorem. There everything is
It
definable.
is.
Okay.
You can give an explicit definition. Maybe I can give a hint. I'm not going to write the proof, but it's quite easy. It's just you need to write it. So C is algebraized by some formula psi, and now you define an equivalence relation that says that for every solution of psi, the formula phi has the same value. And this is going to be how you define the type of C. Now I can even write it by now, I guess. So psi of Y A, well, okay. So this is over ACLEQ of code of X. This algebraizes C. And so now you look at the equivalence relation Y1 equivalent to Y2 if
I think you mean
I'm going
Z1 equivalent to Z2. You're going to quantify over y.
Oh yes, you're right. You're right. You're right. You're right. You're right. Thanks. That's because I didn't prepare it. That's why I wanted to leave it as an exercise to e-type. But if and only if for all y realizing psi, yes. So this is going to be definable, but then we are going to apply the yes. So this is variable x. This implies so you fix theta x y z. You want to find a definition for it. This implies that for all y1, y2, y1 and y2 of psi implies theta y1 equivalent to theta y2. Yeah, this is an equivalence relation, and now you quantify over x. Okay, so this is a formula.
You mean theta of yz1 equivalent to theta of yz2?
Yes, you're right. Thanks that you're here. So sorry. S implies theta of yz1 equivalent to theta of yz2.
Well, to be honest, you taught me that trick, so.
Yeah, I know, but you remembered it and I forgot. So I claim this is a definable finite equivalence relation. And if you take the class of so over ICLEQ of X, every class is in it, and the classes allow you to define when Y is true over a given Z. But if you think a bit about it, it really is a slightly backwards version of the finite equivalence theorem. Yep. Now maybe keep the propositions. Yes, thanks.
So would it still needed stably dominated types?
Yeah, so Udi codes the so the way Udi computes the code is by saying that every definable type lives in a gamma parameterized family of stably dominated types. And so he codes stably dominated types, and then does some definable compactness magic to say that this gives you code for your type. But we'll avoid that part by just computing the canonical basis by hand. And I should stop saying that things are easy because they're not. But I mean, the going to the algebraic thing seems weird, but it's really a theorem that we all know, and we don't know we know.
Sorry,
the thing, the exercise.
yeah, but you do that. This is somehow syntactic.
Well, I mean, I gave a formula, but you can just
Yeah.
you can also just see that there's a finite equivalence relation involved. Right. Yep. Yeah, last time at some point, one time I tried to write on the web thing, and it wasn't a good idea. Did you? Yes, you did this one also. It's because I used the one we are not supposed to use.
I use it all the time.
Well, yeah. The problem is that then you control all three of them at the same time. Which
Yeah.
is- What? Ah. No, because now everything is over there. Everyone? Rahim? Christian? Okay. Zoe? Can I start? Thanks. So, in the little time I've got left, I thought I'd have more time. Let me explain, at least let me try to hint at how you prove 1 and 2. I have really no idea how I'm going to manage, but well, I mean, 1 I'm going to manage, 2 not so much. So in ACDF, how do you prove 1? Well, this is far from the hardest part of the proof because well, if you have X that lives inside K of 1, then X is a finite union of Swiss cheeses. Oh, okay. Let me write it explicitly. X equals the union over I of the BI minus the union over J of the BIJ. And in fact, remember, we proved that the Swiss cheese decomposition is canonical under certain hypotheses. And so we may assume that the BI and the BJs, the BIJs, are actually algebraic over the code of X. This is exactly what's implied by choosing the canonical Swiss cheese decomposition, because now the Swiss cheeses are unique. What?
You mean that their codes are algebraic?
Yes, okay. I tend to consider balls as points after a while, but you're right. Yeah, so what I mean is that they're definable over this. And now just take B0 and take the generic type of B0. This is definable. And so when I defined the generic of a filter, I didn't say that it was definable because in general it's not. But when it's the generic of a ball, it is, because a formula is true if and only if it's true on B and not on finitely many subsets. So you can write this. So this is ACLEQ of code of X definable, and it concentrates on X. Oh, you could actually, I chose B0, but you could choose the one, the generic of any BI works. So that's one. One is pretty straightforward. Two is where things go.
Can you explain again why it's definable? I mean, it's definable if you want to say if a formula is amenable or not, but if you have a general formula, then.
Well, maybe the easiest way to see is if you take B any ball, so what you just said, if you take B any ball, eta B0 implies X in B. If and only if what is it? It's B0 is included in B. But now any formula, any formula is well, if you want the type on when you know the type for balls, it generates the full type. So this tells you that the full type is definable. If you want, there's a hidden compactness that if you have a family of definable sets, the Swiss cheese decomposition, the number of things is bounded in the family, and so you can just look at what happens to balls, and it works. So in general, if you have a partial definable type that implies a complete type, then the complete type is in fact definable. I mean, if you have a definable phi type that implies
every definable set is
yes, is a Boolean combination. But the thing is that a priori you'd be worried that you'd have to that the numbers could change, but they're bounded uniformly in family, so there's no problem. So what is so they're bounded uniformly in family, and so now what you can say is I have my X, I write it as a Swiss cheese with the bounds, and now I check which balls are in the type or not, and that is going to tell me when X is in the type or not. But this really has nothing to do with Swiss cheeses anymore. It just has to do with the fact that if you have a phi type which is complete and definable, well, which generates a complete type and is definable, then the complete type itself is definable. This is a completely general fact. Okay, so that was one. So two now. How do we compute canonical basis of definable types? So let's see. So let's take it inside. So once again, since K is dominant, we can assume it concentrates on Kn, be a definable type on K to the n. And so now there's going to be a series of reduction. And so essentially, it's the idea of the proof is a bit like the proof I quickly sketched about ICVF. We have a type a definable type, and what we want to so if we if we are in ACF, what we want to do is code the underlying ideal. The thing is that here now we're not going to get an ideal. What we're going to get is a valuation on a vector space. So I need to define that. Okay, so if K V is a valued field, and V is a K vector space, the valuation on V is a map W from V into some sigma, where Vk cross X. So this is a group, remember, X on sigma. Sorry, this is an ordered X on sigma as an ordered set. Remember, this is ordered, so we want the action to be ordered. So you can guess what that means. It means that if you act with things that are in the order on things that are in the order, you stay in the order. And such that. So actually, sorry, once again, I put an infinity. Now, let me write the axiom correctly, because that would be annoying otherwise. Yeah, so for all, yeah, so this is just ordered action. Yeah, so it's scalar multiplicative. So if I take lambda in K and X in V, V of lambda X, no, W of lambda X is V of lambda acting on W of X. And now we have something for addition. So if I have xy in V, W of X plus Y is greater or equal to the min of W of X, W of Y. And last, so maybe I should, yeah, V W of 0 is infinity. So note that I have not required that 0 is the only thing sent to infinity. So maybe I should call that a semi-valuation, really. But okay, and so now if P is a definable type on K, for all G positive, I can look at the vector space Kx D. So here X is an n tuple of variables. So this is X0, well, X1, Xn. And here it's you choose one notion of degree, whichever you want, but for example, total degree. I mean, so depending on the notion of degree I take, if I take the notion of degree, which is the maximal degree in each of the xi's, then this is just K D n plus 1. If I'm, no, sorry, the contrary, n d plus 1. This is this vector space. I identify it with it. And I say, and I define a valuation on it, VP, maybe W. Oh, okay. VP of P. So actually the valuation is defined on the whole of K of X, but I wanted, it's not really definable. What's definable is when you look at finite degree things. So VP of X is greater or equal to VP of Q if P says so. So I haven't quite defined what sigma is, but knowing this relation allows you to define a sigma that works to make it into an actual valuation. Okay, it's the sigma is going to be the order associated to this pre-order. And you can check this is a valuation, and it's actually a definable valuation on k to the n d plus 1. So what do I mean by that? I mean that sigma is an interpretable set, and the map is interpretable in ACVF using the code of P. So V of P, well, so I should really call it V of P, comma D, because there's a whole family of them. So V of P, comma D is code of P definable. Okay, so so it doesn't seem like progress, but I've reduced my problem of coding a type to the problem of coding a bunch of valuations. Now, how do we code? Coding a valuation W on k to the n. Well,
And this is by quantified elimination. I mean, the fact that you enough to code.
So quantified elimination it's also you're right. By quantified elimination, knowing all, so the family of all the VP, comma D, this family determines P. All right. So how do I code a valuation? Well, I'm going to show that well, so there's a first claim that I'm not going to prove, and it's really, or maybe I should prove it. It's really the crucial part here is that well, maybe I should write a few things. So when you have a valuation on a vector space like this, the action of VK cross on sigma has finitely many orbits, has at most n orbits. You can see this because you can check that if you have elements, I guess yeah, maybe I should, here I didn't assume it was subjective, but if I look at really what happened, the really interesting things. So if I look at the image of W, it contains at most n orbits. Why? Because if you have n things, if you have n plus 1 things with valuations in distinct orbits, there will be linearly independent. Because if you're in distinct orbits, in fact, the min has to be an equality. And the claim is that every orbit.
Wait, sorry. What is n? N is just the number of variables?
N is the size of the vector space.
Oh, okay. And there was another n.
There was another n just before.
Yeah. Okay. Sorry. Now it makes sense.
Yes, you're right. So yeah, I changed my notation. I'm sorry. Every orbit contains a code of W definable element. So this is a bit tricky, and but it's a wonderful trick of Will, and if I have time, I'll explain what's going on. But somehow you can find elements in each orbit, and once you have that, so let's call them gamma I. You can define a module Si, which is the set of all x's in Kn, such that v of x is greater or equal to gamma I, this is an O module inside K of n is an O module. So I'm not claiming it free. I'm not claiming anything about its rank. I'm just claiming it. I'm just saying it's an O module. This is easy to check because of multiplicativity of the, well, addition and multiplicativity. I mean, the fact that it's a valuation. Oh, it's called W, by the way. This is an easy check. And I claim that if you know all the SIs, you know the valuation. So it's an O module and it's definable. And it's code of W definable. And the other claim is that, in fact, W is code of SI definable. Why? Because if you know, how do I want to explain it? Or maybe I'll leave it as a claim for now.
Maybe let's try to finish now.
Yes. And so now we are down to trying to code O modules. So I shouldn't probably not have called it S because S was my name for lattices. But M is used all over the place. What's a good name for a module? R to code an O module, a definable O module M inside of K. And now we do something that may appear completely silly, but we define a valuation. So we define V to be the set of x's in K such that there exists a lambda such that lambda x is in R. This is a K vector space. Sorry, in Kn. This is a K vector space inside Kn.
So how is that?
Code the definable O module. Oh yes, I decided I wouldn't call it M because it's a model, and then I forgot I said that. Sorry. Yes, so this is vector spaces, the things that never, whose lines never encounter the module. And you define evaluation W on V by W of X is the supremum of the lambdas such that lambda X, supremum of, no, infimum. Lambda is in K. Yes. Sorry. Yes. We're trying to we're defining a subvector space of Kn. So I wrote it the other way around, but it's the same thing. So it's the supremum of lambda such that X is in lambda R, which I guess is this supremum of the V lambdas. So it's just because otherwise you have the inverses around. And I claim this is a valuation. but we've gained something from before because now it's a valuation whose valuation set is actually gamma itself. So this is what we call the strict valuation, or what we'll call the strict valuation. This is a strict valuation on V, which lives inside K of n. And I claim that if you know this valuation, you know the module. This is not too hard to see because the module is exactly, well, not quite, but
Silvan, how do you see that this V is actually closed under addition? Is this obvious?
what?
Why is V closed under addition?
You have to check it.
Oh,
But you use the fact that R is a module to see that. No, it's, I mean, there's things to be checked. Ah, yeah, no, sorry. No, that's what I was starting. The valuation is not enough to know the ring, sorry. So you have a valuation, and so you can define two things. You can define V positive, which is a module, which is the set of all things such that W of X is positive. So it's the set of all X's with W of X positive, and V of strictly positive, which is the set of all X's with W of X strictly positive. And so you can check two things. R is in the middle of those two. So R is contained in V positive, but contains V strictly positive. And in fact, so this implies that R is determined by its image in V strictly positive, in V positive, not V strictly positive. Oh, yes, sorry. No, because for example, start with M inside of, so the maximal ideal inside of K. No, that's V strictly positive, and that's V positive or equal. No, you're right. But yeah, because you don't quite detect the difference between O and M yet, because you've taken a sup. And this thing here is a K vector space. A little K vector space. And so now we're almost done. Well, modulo not proving anything. Let me finish. Maybe let me finish. What? Oh, they're all. Yeah. So the point is that V positive is in fact a lattice of V. So V is a vector space, so it has dimension at most n. And V positive is in fact an O lattice of it. So it's a free O module of maximal rank. And this is n times V positive. So now modulo. How do I want to do this? So now, by another witty remark of Will, which is that any subvector space of Kn actually has a definable basis over its code. There are this. I mean, I don't have time, but this is a very nice remark, and it's very important. But so V has a basis of code of V definable points, definable vectors, which equivalently means that over its own code, it's isomorphic to a certain power of k. So since everything we're doing is canonical, we may actually assume that V itself is a power of k. And now we have a valuation on Kn, an actual valuation on Kn, and a strict one, so it has the right gamma. And so now we can apply the fact that since K is elementary equivalent, well, since a CVF is definably spherically complete, in other words, any model of a CVF, not in other words, but in that particular case, because any model of a CVF is elementary equivalent to one that is spherically complete, or maximally complete, same things. That implies that we can find a basis in V which has very specific form. So there exists a basis of V such that a basis BI n such that V of the sum of the lambda I BI is actually equal to the minimum over I of the V lambda I BI. I think I change between V and W all the time, but yeah, it was called W.
So now V is a definable valuation on Kn,
Yes.
which is not our original valuation.
No, but because it's strict now.
And no, I mean not even val, not even the original.
No, because it's on Kn anyway.
Yeah.
But up to a choice of basis, it is essentially val. Okay. So what this says is that that V positive is actually is an element of Sn. Okay. And V strictly positive is M times V positive. So now what we're left with doing, the last step is we're given a sub-vector space of S mod MS. So let's call that S. So if we look at, we have the projection from V into S mod MS. And what we're left with is, we said that R is entirely determined by its image here. So pi of R inside of S mod MS is a sub K vector space. So once again, millions of things to check. But this is just because you're taking an O module and reducing it mod M, and so you get a sub K vector space. And so now we are down to coding sub K vector spaces of certain vector spaces. And this you essentially know because well, if you know about Grassmannians, you know we can do that. If you don't know about Grassmannians, then you don't know how to do that. But essentially, the idea is that let me finish. I think I'm very much over time, but I just maybe want to quickly explain how we finish. So we have W, a subvector space of S mod MS. And so what you do, this is dimension, so this was dimension N, this is dimension something, let's see D. And you can look at the nth exterior power of this thing, which lives inside it's the tensor product of itself n times. this can be naturally identified with so this is the same as S tensor D mod MS tensor D, which is naturally this is a lattice, so we can, this is still an object we know about. And so now, why did we do that? Is that because now, if we take the exterior power of W inside here, this is now dimension 1. And if we know this dimension 1 thing, we know this thing. That's the magic of exterior powers. So now we're down to coding dimension 1 things inside a vector space. And this we do by induction on the size. So essentially what we've just done is that we may assume that D is equal to 1. And now what happened is that this thing here has flags. So it is, we have a sequence. So let's call this W. Did I already have a W around? Oh, well, small w, I guess. But we have a sequence W0, W1, W. I already had the W, sorry. No, yeah. I should not be doing that. I'm running out of letters. You. Where these are all canonical, these are all definable over the code of U, and each time the dimension goes up by 1. So this is 0, and each time the dimension goes up by 1. And so now if you have a line inside of, and this is U. If you have a line inside of something like this, it actually lives in one of the dimension 1 quotients. And so what you're left with is just, and this completely determines the line. No, not quite. But yeah, I think I've, you can find all the details explained quite nicely in Will's proof, in Will's paper, but yes.
So you use the TNs here, what did you use the essence?
Because I need to know about this thing all the, I mean, I need S. So here now.
So you use the essence for only to parameterize the TNs.
Yes and no, because if your W is everything, so here if your R is V positive, you're coding it by just, you don't need to do the last steps. So there are things you need to code, some things that actually come from the essence. It's just that here I got an element in Sn, but now it's a real point that I can work over with, and so that's why I stopped worrying about it being over what it was definable, because it's defined over itself. Yeah, so the SNs are here to parameterize the Tn, but it happens that it's also, I mean, if you have the Tns, one imaginary of the Tns is the SNs. Okay, I'm sorry, the end was maybe incomprehensible. But essentially, the last step is really just the Segre embedding of Grassmannians. This is just what we're doing.
This is the last lecture, so maybe we can thank him for his. Next week, Zoe starts with the last 4 lectures of this module. We'll certainly announce them as it happens, but next week it's normal. So. Yeah, but not next week. Next week it'll be.
Next week is on Thursday.
Yeah.
After that.
Let me also remind you that this afternoon we have the special seminar that Dave is giving. So at 2 o'clock, right? Yes.
Oui, oui. Bah, en fait, le